Hello, welcome to 4.3 Riemann sums and the definite integral. Okay, in section 4.2, the area under the curve was divided into rectangles of equal base length. These intervals can also be called partitions. The partitions were of equal length for reasons of computational convenience. In this section, we'll explore partitions of unequal lengths, and it can be convenient that way as well, to have unequal lengths. Okay, so it says evaluate the limit. So the limit as n goes to infinity, the sum I goes from 1 to n of f of ci delta xi over the region bounded by the graphs of f of x equals a cube root of x, y equals 0, x equals 0, and x equals 1, where ci, they give us a hint, is I cubed over n cubed, which means this is not going to be a standard width. As n gets bigger, the denominator gets bigger. So what we're looking at is this kind of a curve. So our delta x is going to be ci minus 1, which is going to be I cubed over n cubed minus I minus 1 cubed over n cubed. This is I cubed minus, this quantity would be I cubed minus 3i squared plus 3i squared, plus 3i, excuse me, minus 1 over n cubed, and that's going to be I cubed minus I cubed plus 3i squared minus 3i plus 1 over n cubed. So the I cubes go away, and we're left with 3i squared minus 3i plus 1 over n cubed. So that becomes our delta xi. So we have non-equal widths here. So the limit as n goes to infinity of the sum I goes from 1 to n of f of ci delta xi is going to be the limit as I goes from 1 to limit as n goes to infinity of the sum I goes from 1 to n of what? We have the cube root of I cubed over n cubed. This is where it's convenient to do it this way because the cube root of I cubed over n cubed is just I over n. But then times our delta xi, and our delta xi is going to be 3i squared minus 3i plus 1 over n cubed. So this part is our delta x. This gives us the limit as n goes to infinity of the sum I goes from 1 to n of I over n times 3i squared minus 3i plus 1 over n cubed. Now n times n cubed is n to the fourth, so this is the limit as n goes to infinity of 1 over n to the fourth times the sum of 3i cubed minus 3i squared plus I as I goes from 1 to n. Now we're going to look at each of these. We'll have the sum as I goes from 1 to n of 3i cubed minus the sum as I goes from 1 to n of 3i squared plus the sum as I goes from 1 to n of I. We're going to get this I cubed, I squared, and I from our formula from the last section. This becomes the limit as n goes to infinity of 1 over n to the fourth of 3 times, from this 3, I cubed is going to be n squared times n plus 1 squared over 4 minus 3 times n plus 1 times 2n plus 1 over 6 plus, and from the I, that's n times n plus 1 over 2. Okay. So from the first part we have 3/4 times, if you multiply this out, you have n to the 4th plus 2n, well, maybe I'll do this in another step, n squared times n squared plus 2n plus 1 minus, and then the 3 and the 6 can reduce. We saw this before. It's going to be 2n cubed plus 3n squared plus n over 2. And from here we have n squared plus n over 2. Now if I bring in this 1 over into the 4th, we end up with the limit as n goes to infinity of what? 3/4 times, multiplying this through, that's n to the 4th plus 2n cubed plus n squared over n to the 4th minus 2n cubed plus 3n squared plus n over 2n to the 4th plus n squared plus n over 2n to the 4th. Now in each of these cases, except for the very first case, we have a greater power in the denominator than the numerator, so n cubed over n to the 4th, n squared over n to the 4th, n over n to the 4th, this whole thing goes to 0. N squared over n to the 4th, n over n to the 4th, that's going to go to 0. In fact, that part's going to go to 0 too. That's going to go to 0. So the only thing that makes a difference is this n to the 4th over n to the 4th gives us 1. So our result will be 3/4 times 1, which is 3/4. So this area under this curve is 3/4. Okay. Whew, that was a little bit of work. So feel free to pause it if you'd like. I'm going to go on to the next page. Again, the definition of the Riemann sum. Let f be defined on the closed interval AB, and let delta be a partition of AB given by a is less than x1, x0 less than x1 all the way through to xn less than b, where delta xi is the width of the ith subinterval, so there could be varying widths. If ci is any point in the ith subinterval, then the sum as I goes from 1 to n of f of ci delta xi is going to be called a Riemann sum of f with a partition delta. So ci be some point within the interval. Norm, the width of the largest subinterval of a partition delta, denoted with these double lines on either side of the delta. So if every subinterval of equal length, of equal width, excuse me, if every subinterval is of equal width, the partition is irregular, and our norm would be just delta x, which is b minus a over n. That's a regular partition. And the general partition, b minus a over the norm is less than or equal to n. It's the definition of a definite integral. If f is defined on the closed interval from a to b, and the limit as the norm goes to 0, so the norm is going smaller and smaller, and then remember the norm is the largest subinterval as I goes from 1 to n, of f of ci delta xi exists, then f is integrable on the interval from a to b, and the limit is, check this out, are you ready for this? The ground is going to shake, and I know this is recorded, so it's going to shake multiple times, hopefully it doesn't cause an earthquake, but are you ready for this? here's our limit. This is what we've been working with to find the area under the curve. And this area formula for the limit of the infinite sum is the integral that we've been dealing with. Now this is one that's going from a to b. This has limits of integration from a to b, a lower limit and upper limit. So the limit is called the definite integral from a to b. The number a is a lower limit and b is the upper limit of integration. The point is, by doing this infinite sum, we get to the integral. This is the definition. This is a big deal. Now we will do some more of these longer problems to work out, but we're going to get to the point that we could just go to this and use the shortcuts, which is sweet. That's what I was trying to get at. Like in chapter 2, we had to do the long definition of derivative, and then we got to the shortcut. So, be encouraged. Continuity implies integrability. If a function f is continuous on the closed interval from a to b, then f is integrable on the interval from a to b. Okay, so let's do another problem here. Evaluate the definite integral by the limit definition. So we're going to do the long version here. So we're doing the integral from -1 to 1 of x cubed dx. So our delta x is going to be 1 minus -1 over n, which is 2 over n. So delta goes to 0 as n goes to infinity. So in this, ci is going to be a plus delta xi. So if you just imagine, we're going, this is x cubed, we're doing this type of thing from -1 to 1. So here we are, a plus delta xi for any point in the interval. So ci would be, our a in this case is -1 plus our delta x is going to be 2 over n I. And they should say delta x, not delta n. So we're going to look for the limit as n goes to infinity of f of ci delta xi. So the sum as n goes from 1 to infinity of f of ci delta xi, it's the sum I goes from 1 to n, sorry, it's 1 to n, not infinity, of f of -1 plus 2 over n to the I power, no, 2 over n times I, times 2 over n. That's our delta xi, or delta x in this case. I, because it's all the same in this case. I goes from 1 to n of what? -1 plus 2 over ni cubed times 2 over n. And that's going to be equal to the sum as n goes from 1, that was I goes from 1 to n of, now we're going to expand a cubic here. I hope you remember how to expand a cubic. That's -1 cubed plus 3 times -1 squared times 2 over ni plus 3 times -1 to the 1 power times 2 over ni squared plus 2 over ni cubed times 2 over n. So we have as the sum as I goes from 1 to n of -1 plus 6i over n minus 12i squared over n squared plus 8i cubed over n cubed times 2 over n. So we can pull the 2 over n out front. And we have -1, sum for -1, plus 6 over n times the sum as I goes from 1 to n of I, minus 12 over n squared times the sum I goes from 1 to n of I squared, plus 8 over n cubed times the sum I goes from 1 to n of I cubed. negative n. This one sums to be negative n. Sums to be n, but there's negative 1 times n is negative n. Plus 6 over n times n plus 1 over 2 minus 12 over n cubed times the I squared, is going to be a 2n cubed plus 3n squared plus n over 6. Remember how we worked that out before? That's n times n plus 1 times 2n plus 1 all over 6. And then we have, I think this is a squared down here. Yeah. And then we have plus 8 over n cubed times the sum for the I cubed was n to the 4th plus 2n cubed plus n squared over n to the 4th. No. Over 4. There we go. Okay, so where does this take us? If we distribute this 2 over n now, we have 2 times, let's just say negative 2 times n over n plus 2 times 6 over 2 times n squared plus n over n times n is n squared minus 12 over 6 times n cubed, 2n cubed plus 3n squared plus n over n cubed plus 8 over 4 times n to the 4th plus 2n cubed plus n squared over n to the 4th. So in every case, if I take this limit as n goes to infinity of each case, negative 2 times n over n plus 6 times n squared plus 2 over n squared, no, n squared plus n over n squared, minus 2 times 2n cubed plus 3n squared plus n over n cubed. So notice in each case, n over n squared plus n over n squared, it's the highest degree, plus, and then we have 2 times n to the 4th plus 2n cubed plus n squared over n to the 4th. Trust me, this gets better. Now, all the smaller terms are going to go away. So we have negative 2 plus 6 minus 8 plus 4, and not to let you down about this, not to make you sad, think, oh my gosh, what a lot of work for this. That's just 0. But you might suspect that because you have area under the curve equal to area over the curve. And they cancel out. That's how it works. Okay, so that is the Riemann sums. Very long process to get there. And we're going to learn shorter, quicker ways to do that, and you're going to be all excited about it. So, feel free to pause that one. I'm going to go on here. Theorem 4.5, the definite integral as the area of a region. If f is continuous and non-negative on the closed interval AB, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is given by area integral from a to b of f of x dx. So we have a curve from a to b that gives us the area under the curve. So we're going to use the geometric formula to evaluate the integral. We know the geometric formula for the area of a rectangle. So what is the difference here? From 1 to 5. 5 minus 1 is 4. The height is 4. So the area is going to be 4 times 4, which is 16 units squared. Next we have a trapezoid. Let's see here. Y equals 2 times 0 plus 5, that's 5, so this part's 5. Y equals 2 times 2 plus 5, that's 9, so this is 9. So the area for a trapezoid is 1/2 of B1 plus B2 times the height. And B1 plus B2, that's the length of the parallel sides. This is a trapezoid on its side. And the height here is 2. So this is 1/2 times 5 plus 9 times 2, and we get 14 for that. Okay, I'm going to go on to this next problem here. This is a semicircle with radius r, and with the area of, so just the upper half. So area is going to be pi r squared over 2. Radius is r. Pi r squared over 2 is just half of a circle. So if you need to see it this way, think of y equals the square root of r squared plus x, no, minus x squared. So y squared equals r squared minus x squared. X squared plus y squared equals r squared is the equation of a circle. My blue pens are drying out today. Let's see what else I have here. More blue pens. Really, I'd like to use blue because it stands out better than the black. I mean, the black shows up, but it gets kind of dark on the screen. Okay, moving on to page 5. Definition of two special definite integrals. If f of x is defined at x equals integral from a to a of f of x dx is 0. So what we have is we have height, but we have no width. So it doesn't matter how high it is. The height times 0 is 0. And if f is integrable on the integral from a to b, we define integral from b to a of f of x dx as the negative of a to b of f of x dx. So what's the integral from pi to pi of cosine x dx? This follows the first one up here, going from the same thing, a to a. This is just 0. And the integral from 0 to 2 of 2x plus 5, that's going to be the negative of the integral from 0 to 2 of 2x plus 5. And we saw this in example 3b. So that's going to be the negative of 14. And trust me, it pains me not to show you how to work this out. We're going to get there. Be patient with the process. Okay, theorem 4.6, the additive property of additive integral. It says interval property. I think it's integral, but okay. If f is integrable on 3 closed intervals determined by a, b, and c, the integral from a to b of f of x dx equals integral from a to c of f of x dx plus c to b of f of x dx. So given the integral from 0 to 5 of f of x dx is 10, and 5 to 7 of f of x dx is 3, evaluate the integral from 0 to 7 of f of x dx. That's from 0 to 5 of f of x dx plus the integral from 5 to 7 of f of x dx. 0 to 5, 5 to 7 is 0 to 7. That's 10 plus 3, which is 13. Yay! And the integral from 0 to 5 of f of x dx is the negative of integral from 5 to 0. We're going to go 0 to 5 of f of x dx, which is the negative of 10. I'm going to go on now. Theorem 4.7. Okay, properties, last page now. Properties of definite integrals. If f and g are integrable on ab and k is a constant, then the functions of kf and f plus or minus g are integrable. Integral from a to b of k times f of x dx is k times the integral from a to b of f of x dx. And the integral from a to b of f of x plus or minus g of x is the integral from a to b of f of x dx plus or minus integral from a to b of g of x dx. So we're given that integral from 4 to 2 of x cubed dx is 60. Integral from 2 to 4, I keep saying it backwards. 2 to 4 of x dx is 6, and 2 to 4 of dx is 2. What is the integral from 2 to 4 of x cubed plus 4? That's the integral from 2 to 4 of x cubed dx plus 4 times the integral from 2 to 4 dx. The first one's going to be here. 60 plus 4 times, this one is 2. So that's 68. Okay, I'm going to go on down to the bottom of the page here. Preservation of inequality. If f is integrable and non-negative on the closed interval from a to b, then the integral from a to b of f of x dx is greater than or equal to 0. So if it's not negative, it can't be 0. If f and g are integrable, if it's not negative, it could be 0 or more. If f and g are integrable on the closed interval from a to b and f of x is less than or equal to g of x for every x in a, b, then the integral from a to b of f of x dx is less than or equal to the integral from a to b of g of x dx. Okay, we will stop there with that section. That was 4.3, Riemann sums. No, that's tough. I'm with you. Send me your questions. This gets better. This gets really cool. Thanks.